Let's look at exercise 14.13, or exercise 13 in chapter 14, which is our op-amp chapter. This particular exercise is dealing with this non-inverting op-amp configuration. Let me sketch that as we're talking about it. It also is giving us quite a few limitations of this particular op-amp in terms of practical constraints that we now need to consider when we're analyzing this circuit. Here's R sub 2. We're applying an input to the non-inverting terminal. Here is our V sub S of t, and we're assuming that that's a sinusoid in all of these parts. Here's R sub 1. And this particular circuit now is going to give us, if we were interested, this is going to give us a relationship if we were not in saturation or any other limitations. This would be the relationship for a non-inverting op-amp, which is 1 plus the ratio of those two resistors. Our two resistors are actually equal, and they're 100 k ohms each, which allows us to then say that V naught of t is going to be 1 plus 1, or 2 times V sub S of t if we do not have any restrictions. What this particular circuit or exercise tells us is that our supply voltage is actually limited to, let's say, we'll call the positive voltage 4 volts, the negative voltage, and these are what we're plugging this op-amp into. That's what's supplying our power to activate this circuit. We also are told that the output maximum current is limited, and they always are in an op-amp, but this one is I sub 0 max. The highest it can go, if we were thinking of this like a garden hose, as much water as we can get out is only 10 milliamps, and it also can only run so fast, or it can only change voltage so quickly. And our slew rate limit in this problem that we're working with is 5 volts in a microsecond, and that's what we're defining as our slew rate limit, SR. And again, V sub S is going to be a sinusoidal input. In the first part of this problem, it wants us to find the full power bandwidth of the op-amp. And the full power bandwidth is really what frequency signal input will produce an unlimited output signal. And this is given to us in, or the expression or relationship is given to us in equation 36 in chapter 14, which says that the full power bandwidth frequency, which is F sub Fp, is the slew rate value, which is so many volts per so many seconds, divided by 2 pi V sub 0 m, where V sub 0 m is our output maximum voltage. In this particular problem, V sub 0 m is given to us, or it's established by our supply voltages. Let me try to clean that up a little bit. And our supply voltages now are the plus and minus 4 volts, where I called the positive V sub CC, and the negative I was labeling V sub EE, And those two, because they're symmetric and we're dealing with sinusoidal signals, that gives us then our maximum amplitude in these output sinusoids. The most it can be is 4. The slew rate value is really telling us how quickly or how quick the op-amp can respond to voltage changes. In a pictorial way, we could think of this slew rate then in terms of a diagram. We now have a slope where this could be our volts, and this is now time in some amount of seconds. But we are now wanting to know, or that slew rate now tells us, we can get to this magnitude of voltage in so many seconds, or partials of a second. And if we went all the way out to, let's say, 1 second in time, then this particular slew rate that we have would be how large our value could be in terms of voltage. In our particular problem, in this example, we're given that the slew rate is 5 volts per microsecond, or that's 5 volts over 10 to the minus 6 seconds, or that SR is now 5 times 10 to the 6 volts per second. That being stated, again, this slew rate is basically how quickly the time rate of change of our output can occur, which is just related to the derivative of our output signal, and that's how this formula has been obtained. The full power frequency is then this SR over 2 pi V sub OM. SR is 5 times 10 to the 6, 2 pi, and V sub OM, because of our supply voltages, is 4, and so our now full power frequency is that particular expression, or it's basically now 5 over 8 pi times 10 to the 6th. And we now can divide that out, and we end up with 199 kilohertz. If we put in a sine wave of 199 kilohertz, as long as our load resistor is not too small, we should be able to then achieve that particular amplification of 2 in magnitude that our circuit is designed to accomplish. But that's as high in frequency as we can go without having limitations because of asking our system to run faster than it's capable of running. In part B, it wants to know, for a frequency of 1 kilohertz and a load resistor of 1 k ohm, what peak output voltage is possible without distortion. Now we have a 1 kilohertz sinusoidal input, and our load resistor, R sub L, is 1 k ohm. We now have a couple of pieces that we have to be concerned about. From our circuit, we have to worry about the frequency and the load resistor, and the load resistor is going to be what determines how much current we're drawing from our op-amp. And remember, we can only get so much current out of the garden hose of our op-amp. But from our given circuit, we know that our output voltage is 1 plus this ratio of R2 to R1. It was a non-inverting op-amp circuit, and as long as we are within the limits meaning we're underneath our full power bandwidth frequency. We're within our supply voltage limits, and we're also not drawing too much current. Then we will have a gain in our circuit of 1 plus 100 over 100, or 1 plus 1, which is 2. In this particular case, our full power frequency was 199, and we're putting in 1 kilohertz, and 1 kilohertz is definitely less than 199 kilohertz, which says then that we are well within our speed limit. Where our speed limit said you can follow or actually amplify without any loss 199 kilohertz. We're just now in this particular part of the problem asking for a 1 kilohertz signal, so we're well within that, and our full power bandwidth is not exceeded. That's half of the picture, or of the piece. We now need to check to make sure that the load resistor is not too small to allow too much current to be asked for or required from our circuit. Let's now check the current that's drawn by the output load. And to check that current, let's go ahead and assume that we are going to get the maximum gain out of our non-inverting op-amp circuit. Let's assume the maximum possible output voltage, which says that V sub OM, which is V sub CC, which is equal to the minus VEE, that's 4 volts. We assumed a symmetric power supply. That means that our maximum current that we would be asking if we did get up to our maximum peak voltage in our output sinusoid, we would need to divide that by the load resistor R sub L. In our case, we were given R sub L was a 1 kilo ohm load, and we now know then that I sub 0 is going to be 4 divided by 1,000, or this is now 4 times 10 to the minus 3 amps, or that's now 4 milliamps. Well, I sub 0 that we're asking our circuit to produce, 4 milliamps, is enough less, is significantly less than what we can give, so we're not asking the garden hose to put out more than it can deliver, meaning this particular load resistor is not going to require more than what our system can put out, and so therefore our op-amp also, not only does it meet the frequency demands, but it meets the current demand. 4 milliamps is less than 10, meets the current demand of this load R sub L that we subjected it to, and because of that we're not going to have any clipping, and no clipping will be caused from the current. And that current is drawn from the op-amp, maybe I should say that, current drawn from the op-amp to supply our load R sub L. So we're now looking at no clipping will be caused from the current drawn from the op-amp. And because of that, we can actually expect to achieve our maximum output voltage. We can expect a 4-volt max for this required frequency, which was, now I've forgotten what our frequency actually was. Our frequency in part B was 1 kilohertz. And from this load, for this frequency and load, where our load was R sub L equal to, in this particular part, 1 k ohm, or 1,000 ohms. That's part B. Now let's look at part C of this problem, or exercise. Part C asks us to vary this up a little bit. Actually, it says for a frequency of 1 kilohertz and a load of 100 ohms, what peak output voltage is possible without distortion. The only change that we've done in this part is we've now reduced our load in terms of its resistance, and that means it's going to draw or require, which part are we on? Now we're on part C. I'm trying to get ahead of us. We're now looking at part C. And this is different from part B, only that now we want to suppose that V sub S of t has a frequency of what we had in part B. Now we have a frequency for V sub S of 1 kilohertz and a load resistor R sub L. Now this is smaller than what we had before. Because our frequency is the same, we shouldn't expect any change there, and so we should be well within our full power bandwidth. The frequency is the same as in part D, and it is well within the full power bandwidth. Now what we need to do is check the current draw. And we'll approach this just like we did in part B. But now we have a smaller resistor, load resistor, and that's going to demand more current, and we might expect a little bit of a different or change. Now what do we have? We're looking at our I sub 0. We're still going to assume a maximum value of our output voltage, which is determined by our supply rails of plus and minus 4. Here's our load resistor, which is smaller. It's now 100. This is now going to be 4 times 10 to the minus 2 amps, or that's now 40 milliamps. Well, that should start raising a flag because 40 is bigger than what our op-amp circuit is capable of delivering. Our garden hose can only deliver 10 milliamps. Because of that, then, this load does demand more current than the op-amp is designed to deliver, and the op-amp can deliver. And this is going to then cause some clipping. So the peak current for this load will be limited by by the max current this op-amp can supply. And the maximum voltage that this op-amp can supply when it reaches its current limit is going to be the current limit max times the load resistor, or our V sub OM actual or restricted is going to be the maximum output current that our op-amp will deliver times the load resistor R sub L. Our output maximum current is 10 milliamps, which is 0.01 amps. Our load in this case was 100 ohms, and we take 1/100th times 100th. That says now that we have a 1 volt restriction on our output waveform. We're going to clip our output sinusoid at 1 volt if we now try to drive our system with this particular light of a load. It's going to pull too much current, and that current, when it clips or reaches its maximum, is going to clip the output voltage. So the output waveform will be clipped at 1 volt, and if you want to see what that looks like, you could then look at figure 1426. Obviously you're going to have a different magnitude, but this is just an example of what you might expect for clipping due to exceeding the maximum current. If I could draw it, let me see if I can give you a little bit of a feel for what that might look like if I can sketch something. Suppose that we now have our ideal output. That's what we would like to accomplish, and because of our supply voltage, this, if the frequency wasn't, or if our current wasn't limiting things, we would then be able to get to a 4 volt maximum value, both positively and negatively. Here's time. But what we actually find is that because of the light load, we can't do that in this case, and we're actually going to be clipped at 1 volt. And then our voltage will go up, it'll get clipped at 1, it'll come down, and it'll get clipped at -1, it'll go up again to 1 and get clipped. So here's 1 and here's -1, and that's what it would look like. The red curve is the actual response when we have current restrictions or limits imposed by trying to draw the maximum current for that low of an output resistor. Part D for this particular problem says, for a frequency of 1 megahertz and a load resistor of 1 k ohm, what peak output voltage is possible without distortion? Well, what we need to do is recall how we derived, or recall the derivation of the full power bandwidth and what we were doing there is we were saying, because of the slew rate limit or the speed of our system or of our op-amp circuit, we can only achieve so much slope change, or we have a maximum time rate of change of our output voltage with respect to time. And if I could say this in sort of sequence, the first sequence is that our signal's time rate of change, which is just the derivative of our output voltage, is actually limited by this slew rate limit, or the op amps slew rate limit. If we now assume a structure for our output voltage, we can derive this relationship that we had, or that exists in equation 36 in chapter 14. Let's just say that we have our output voltage as a sinusoid, and it's now some Vmax sine at some frequency omega t. Luckily, we've had our calculus, and we can now differentiate that sinusoid with respect to time. So its time rate of change is dv naught dt, which is Vmax. Derivative of sine is cosine, and we now need to differentiate the argument of that cosine with respect to time, which allows us to then pull that omega out front. This now says that if we look at the magnitude of that derivative, that's equal to Vmax omega, because cosine maxes out at a value of 1, so the maximum that we can expect is the amplitude of that derivative, which is omega Vmax. But remember what omega is. That's simply 2 pi f. And we need that to be, or it will be limited by how the speed of our op-amp circuit, which is our slew rate limit. We can now solve this, instead of in equation 36 where we solved it for the frequency for our full power, we can solve this for our maximum voltage. If we do that, our maximum voltage now is going to be the slew rate value divided by 2 pi f. If we plug in what we know is true for this particular example, we have 5 times 10 to the 6 for our slew rate, volts per second. We have 2 pi, and we're asked to be putting in a 1 megahertz frequency. That's 10 to the 6. Conveniently enough, these 10 to the 6's cancel, and now we have basically 5 divided by 6, or if we do the more precise computation, that ends up being not 80%, but 0.796 volts for our maximum output voltage. And that's what we could expect for the peak amplitude in our output waveform when we were pushing to go to 1 megahertz for our input sinusoid, and that's what our output sinusoid would be, but it would be restricted to be less than 0.8 of a volt, or 0.796 volts. Finally, the last part of problem or exercise 13 in chapter 14 is to, if the resistor on the load is 1 k ohm and V sub s is again this 1 megahertz sine wave, they want us to sketch the steady state output waveform to scale versus time. Well, if we have V sub s equal to this 5 sine of 2 omega t, where we have 2 pi f, and f is 1 megohm, there's our omega t. What we want to do now is our output voltage, if this was an ideal circuit without any limitations, this would be 2 times V sub s of t, and that's going to be 10 times the sine of 2 pi times 10 to the 6th t. Well, let's now see if we can sketch this. If we were sketching this properly, and it says to do it accurately, but I'm going to try to do it by hand, but I'll at least start to get some of the information down that I need to. My omega frequency, which is 2 pi f, is also 2 pi over t. And this allows us to say that our frequency is just 1 over the period, or we now know what our period of this waveform is, and this will allow us to get a time axis. We now know our period is 1 over f. F was 10 to the 6, or 1 megahertz, and so now we know that our period is actually 10 to the minus 6, or 1 microsecond. That's the period of our input and output sinusoid. Our output is going to have a maximum amplitude of 10 if we didn't have any restrictions. And let's now just sketch that for a hypothetical unsaturated or an unlimited waveform. We've now determined that this period is 1 microsecond in time length. This amplitude is 10. And what we have to remember, though, is that our slew rate was this 5 times 10 to the 6 volts per second. Or that was 5 volts over 1 microsecond, which says that we would get to halfway up here if we kept going in the positive direction in 1 microsecond. We would get to a value of 5 volts. But we're not getting there, are we? We're actually just going as far as, now we finally have caught up to our actual output. The demand is what the green curve is saying. What our system, poor system, can't run that fast. It can only get us to that point right there before it starts reversing direction. Once it starts reversing direction, now it heads back and starts moving with the green, but it can't keep up with the green. The green's going too fast. And now it tries to go down another 5 volts from that particular spot if we kept going in that direction. And this now, if you look, this point is going to be halfway towards the period. So here is half of a microsecond. And we're roughly then, by that point in time, we are roughly at halfway. So we're now getting to 2.5 volts before we have to switch direction. We finally caught up, but now when we get over here, we're roughly going to be not at 5 where we would like to be over here in 1 microsecond, but we're only halfway there. And this is not going to be very accurately drawn, but that's now where we would get to. And I hope you can see that this is going to now be this triangular waveform that's oscillating or varying between a maximum amplitude of, or its output waveform really is limited to 2.5 volts.